This first module in BAE 417, we're going to look at internal combustion engines. Specifically, as you can see, we're going to look at basic engine function. We're going to talk about engine performance. In a lot of ways, we're building ourselves up for our first laboratory where we're actually going to get down and measure the power output from an engine. Look at the nature of that power output, compare it to specifications for a vehicle. We're actually going to be looking at an agricultural tractor and how much power we get out of it. And so that's kind of where we're leading up with this first part of the class. But as we go through this, I want you to be thinking a little bit deeper. You're engineers, and I want you to start thinking like engineers, because the internal combustion engine, really, when you look at the fundamental operating principles, it's an early 20th century technology that hasn't changed fundamentally since then. We've done a lot of refinements and revisions and made it better, but it's still the same basic functionality. And when we start looking at the efficiencies, I think you're going to be really shocked at how bad the efficiency is. Essentially, we're taking a liquid fuel that has energy in it, thermal energy, and we can ignite that fuel, we can recover the energy out of that, and we convert that energy into a mechanical power. In this particular case, we're looking at a rotational power. And so how we do that and how much of that fuel energy that gets converted into that mechanical energy, I think you're going to be shocked at how poorly that efficiency is. So as engineers, we should always be thinking in the back of our mind, is there a better way to do this? Is there a more efficient way to come up with this mechanical power that we need for mobile equipment to make it happen? So as we go through, let's do that. So let's start looking at functionality, and we're going to start and focus first off on the four-stroke engine. And you can see here on the left-hand side, there's an animation of this engine that is moving. And we have the four different fundamental strokes highlighted in these four pictures here. And they're all happening at the same time as that engine's moving on the left there. But the first stroke we talk about as the intake stroke. So this is the intake. And in this particular stroke, the piston is coming down, and you'll see it on the animation on the left-hand side. The intake is when the gas is coming in from the right-hand side of that engine. So the piston is coming down, it's drawing a vacuum, it's bringing gaseous material into the engine. The second stroke, then, the piston goes up. This is what we call the compression stroke. And in the compression stroke, we're actually taking that gas, compressing it to some point, to some pressure, and then at the top of that stroke, or very near the top of that stroke, when that piston gets to the top, we're going to ignite that fuel. When we ignite that fuel, it burns thermal expansion. It's going to push that cylinder down, push that piston down, and then we get the stroke, what we call the power stroke. And that's where the piston comes down, the exhaust is burning, it's expanding, it gives us the power, pushes that piston down. And then when we get to the bottom, now we have all this burnt fuel inside the cavity above that piston, and we've got to get rid of it, those exhaust gases. And so then we have the exhaust stroke. And this is where the piston goes back up and pushes it out. And so you'll see this on the animation over here on the left-hand side where you have the red hot gases that will be pushing out. So again, the fuel comes in on the intake stroke. We'll see it here when this turns blue. We have a compression stroke, the power stroke, and then the exhaust that pushes it back out. A couple things I want you to notice. You look at the valves on the upper side of this cylinder. So you can see these rods moving up and down. There's actually a rotating shaft on the top. This rotating shaft on the top we call the camshaft on an engine. That camshaft, you can see it has a high lobe on it, so as that lobe comes around, it pushes down on that valve, and that opens the valve and allows the gas either to come in or to come out. So this on the right-hand side would be the intake valve. The left-hand side then would be the exhaust valve. So that's the valve that lets the exhaust come out of the engine. Okay, so this is a four-stroke cycle that we see working. Fairly simple, fairly basic. And again, it's what was developed back in the early 20th century to make the thing work, to make an engine work. There's been a lot of refinements on that, and we could spend a lot of time looking at details, and we won't in this class. Again, we're looking at an overview, fairly broad picture idea of how these things operate, but that's the fundamentals of the four-stroke engine. Four strokes, intake, we pull the gas in, we compress it, we have a power stroke, and then we have the exhaust that we have to get rid of. Okay? Let's go a little bit more detail here and talk about engine dimensions. So let me look at the engine, and we characterize the engine by its displacement. And so we talk about so many cubic inches, so many liters, if you see it on automobiles and everything else. How is that defined? So let's look at the graphic here, and you can see this same piston we have, and this piston is shown at the very top of its stroke. Okay, and this we actually call top dead center, TDC, or sometimes head dead center, HDC. Okay, so when it's at the top, we say it's at the top dead center or it's at the head dead center. Okay, and so I'll make a mark here for where the top of that piston is right now. Now, when that crank turns around, as you see in the bottom here, the crank is going to move around. It's going to come down to the bottom. The crank will be located down here. That will pull this piston down to some location down here. Okay, this would be the bottom of that, so we would call this the bottom dead center. Okay, or sometimes we call it crank dead center, CDC. So either bottom dead center for BDC or crank dead center, CDC. The distance then in between these two is what we call the stroke. So that is how far that cylinder moves in one stroke. Okay, so that's the stroke. That gives me the displacement. So the displacement then, when I define the displacement of the engine, it is going to be based on that stroke. Okay, so the displacement, and I'll call that, and let me look at my notes to make sure we stay consistent with your textbook and everything. We call this V sub C, and V sub C then is the displacement, or the volume that is displaced by a cylinder. And it's very simple. It's just a cylindrical equation. So pi times the radius of that cylinder, pi r squared, that gives me the area, times the length or the height of the cylinder, which is going to be the stroke. Okay, so that's that distance that you see over there, the stroke of the cylinder. So it really has nothing to do with the dimensions or what else is going on in the cylinder. Now, look at the top of the cylinder. You can see at top dead center, as we're shown here right now, there is some space on the top of that cylinder. Okay, that space up above the cylinder we call the clearance volume. Okay, so we'll call that V sub CL. And that's the clearance volume. Okay, so when that piston comes all the way to the top and gets to the very top of its stroke, you can see that there is some space up there. The volume does not go to zero. Okay, that clearance volume is going to be pretty critical in how we define what happens or what goes on in the cylinder to get to the compression ratio, which is what we really need. So let's define something else. Let me define the total volume, V sub T, and I'll call that the total volume of that cylinder. Okay, and the total volume is equal to the clearance volume, V sub CL, plus the V sub C, which we say is the volume of the cylinder, so the volume that is displaced by one cylinder. So that's the total volume. Okay, now the critical thing, again, for engines and different kinds of engines, we're going to start looking at spark ignition, gasoline and diesel engines, which are compression ignitions. We need to understand what the compression ratio is. Okay, so the compression ratio is defined then as the volume total, the total volume, divided by the clearance volume. All right, so be clear about that. So it's the total volume. So the total volume, so that's the amount of gaseous space, if you will, above that cylinder when it's all the way at the bottom. That's the total volume of that cylinder. The ratio of that to what's left after we squeeze it all the way up. So that's basically telling me how much I'm going to take this gaseous material and compress it. So what is its compression ratio? How much is it going to compress? And that's going to be critical to how an engine functions. Okay, so that's the total volume, the compression ratio. Now, one more thing I want to mention that then we stay very clear about when we talk about the volume of a cylinder, okay, V sub C, and we define that up here. That's the volume of one cylinder, and we'll see, and I'll show you some pictures here in a minute where we can have multiple cylinders in one engine, so they're connected together. And so we'll also define the displacement for an engine. We'll use V subscript E, and the displacement for an engine then is the volume of a cylinder, displacement of one cylinder, times the number of cylinders. Very simple. So if we have an 8-cylinder engine, your V8 pickup truck, so you can get the volume of one cylinder and know what the stroke is, what the diameter or the radius of the piston is, multiply that by 8, that gives you the displacement, the total displacement of your engine. Okay, so let's take a look now. So now that we have that defined and understand what's going on there, let's look at how we actually ignite this fuel, and we're really going to look at two fundamental kinds of engines. We're going to look at a spark ignition engine and a compression ignition engine. First of all, spark ignition. So let's take a look at a spark ignition engine, and you can see here that the spark ignition, we are going to allow that fuel to compress, and we're going to light it with a spark. And so the picture you see in the middle there is a spark plug, and so right in this area of the spark plug right there, we're going to create a high voltage electrical charge, electrical spark that'll make a spark, and that's going to light the fuel. So in a spark ignition engine, the fuel, that the gaseous material that we bring into the engine on the intake stroke is actually a combination of air and fuel. So it's an air-fuel mixture. So on that compression stroke, we pull in an air-fuel mixture, and then we're going to compress that to some point. And you can see there on the notes that the compression ratio for a spark ignition engine is approximately 10-to-1. Okay, now let me talk about that compression ratio and the fuels here a little bit, because this is kind of critical to understand, especially when we get to diesel and spark ignition and compression ignition engines. Any type of fuel, when I have it mixed with and gaseous in a certain proportion, and if I compress that mixture enough, it will auto-ignite. It'll burn. It'll basically explode. Okay? So when I pull in that air-fuel mixture into this cylinder and I compress it, I want to make sure that it doesn't explode or burn or ignite. Actually doesn't explode, it burns. I don't want to make sure that it doesn't start to burn before I want it to. Because if that piston is still coming up and I get to a high enough pressure, which we get some pretty high pressures in these cylinders, especially when you consider the temperature that these engines run at, I want to make sure that that thing doesn't ignite before that piston gets to the top, because if it does, if it ignites and that piston is still coming up, they're going to have a pressure that tries to put that piston back down. The engine's not going to work well. It may actually stall completely. It's going to rattle it. Very likely it's going to damage the engine if those kind of things happen. So on a spark ignition engine, I want to make sure when that piston comes all the way to the top and I compress that air-fuel mixture, it doesn't get above the ratio that is going to make that fuel auto-ignite. And so that's why the compression ratios on gasoline or spark ignition engines are limited to about 10-to-1. More commonly it's about 8, some of them about 8, anywhere from 8 to 10-to-1 depending on the engine design, how fast it runs, and what temperatures it's designed to operate at. Okay, so that's the auto ignition property. So when that piston gets up there and gets to the right point, now I'm going to ignite that fuel with that spark. And I can control when it ignites, and usually that happens a little before it gets to the top, because it takes a while for that spark to ignite the fuel to start to burn, start to build up that pressure. So I start a little bit early, right before that piston gets to the top, I ignite it, and then when the piston starts back down, now I've got the fuel that's pushing and expanding it, and then it's kind of like that bicycle. So I'm pushing down on the pedal of the bicycle, so that crank on the bottom is like your bicycle pedals. I push down and then let it come back up and exhaust it out. Okay, so that's the compression ratio and why it's important, and the auto ignition of a fuel that we need to keep in mind. We'll come back to that, talk about octane and cetane and those kind of things with fuel in a later module. Those will become important. But how do we get the fuel into the engine? So you see on the bottom, that picture there is a carburetor. And that's typically, especially in older technology, this is typically what we would use. And you can see on that carburetor on the left-hand side, this is actually a well of fuel. So we have fuel that is just kind of sitting in this chamber in here. We have a valve that allows the fuel in. There's a float that sits on top of the fuel and keeps the right amount of fuel in there. From that fuel then there's a small passage, and we'll often call this a jet. Okay, so this would be the jet. So if you hear people talking about jets in their carburetors or something like that, it's basically this size. So we have to carefully control the size of the opening, the size of the jet that pulls that fuel into the airflow mixture. Now in this particular carburetor, we're showing the air flowing down through the carburetor. It can flow sideways, different directions, depending on the design. But you can notice that as the air comes down through the carburetor, we push it through a constriction. So what happens when I constrict a fluid flowing through a place like that? As the area gets smaller, the velocity gets higher. So this fuel is going to be, this air is going to be moving faster as it comes through that constriction. But that also more pressure, hence a venturi. So we basically create a venturi effect in the carburetor right there. So now we can, with that negative pressure, we can actually pull the fuel out of the bowl. The fuel then gets mixed with the air, goes through the carburetor and into the engine. So now we have this air-fuel mixture that goes into the engine. All right, a couple of other controls on here. So we show a throttle control down at the bottom. So this is going to control how much, that's kind of a butterfly valve, a plate that will turn sideways, and that'll restrict how much of that fuel can flow into the fuel or mixture that can flow into the engine. We also have a choke valve on the top, and this controls how much air can come into the carburetor. And on modern engines, this is usually done automatically, but on especially if you get to lawnmowers, stuff like that, they may have a choke on them, or the full open position on your throttle will actually give you a choke position. And what that does is it closes this valve, it limits the amount of air that comes in, and so I have a more rich mixture down here, which means more fuel in relation to the air, makes it easier to start a cold engine. Now, as soon as that engine starts, now that very rich mixture is not going to allow the engine to run very well, so we would open the choke soon after the engine starts. And anybody that runs small engines, you know that's the way you manage those. You put the choke on, you start the engine. It doesn't sound good until you open the choke up, let the air flow through there to get the right air-fuel mixture. Okay, so that is basically how they work, how we get the fuel into it. And again, that's somewhat legacy, somewhat old technology because in a lot of our modern engines, especially most of your automobiles are spark ignition engines. They run on gasoline or ethanol. That's the fuel that we typically use, or a mixture of those two. Those are our spark ignition engines, but a lot of those, they talk about them being fuel injected. And so the carburetor technology is somewhat old and really used mainly on smaller engines now. On most of our new engines, when we have a lot of electronic controls and everything, they're going to be fuel injected, which means instead of relying on the venturi to suck that fuel in, we're going to have a positive pressure pump. So we're actually going to physically pump that air. We're going to inject that air, atomize the fuel into the airstream before the cylinder. So we can force how much fuel goes in there. We can control how much fuel goes in there better and control the performance of our engines in a better way. So a lot of our modern engines now are fuel injected. But again, it's an injection before the cylinder. So we inject it into the airstream so that mixture that goes into the cylinder is an air-fuel mixture. All right, now the last point there that I haven't hit on the slide is the efficiency, and here we go. And we'll come back and look at PV diagrams and some thermodynamics and all that kind of stuff, and you'll see that, hey, the efficiency of these things is 30%. What that means is if I look at the amount of thermal energy that's in the fuel that goes into a spark ignition engine, I can recover about 30% of that in useful mechanical work. Okay, 70% of that, a lot of it is going to heat. So the engine gets hot, and we know we have to cool them off. We have to have radiators and everything, and we'll look at some of those cooling package issues in a little while. But we have to cool it off. So a lot of that stuff is thermal energy. So how can we recover that thermal energy? There's some of the things that we can think about as engineers. Like, can we use that energy for some other reason? And I'll show you some ways that we can do that, where we can recover some of that thermal energy. But that's where we are with the spark ignition engine. Okay. Now, let's take a look at compression ignition engines. They're a little bit different, and again, we go back to the auto ignition properties of the fuel. Compression ignition does not use a carburetor. In fact, when that compression ignition engine is on the intake stroke, it's pulling in clean air. So there's no fuel in the air that it's actually pulling into the cylinder. So we put the fuel in after we compress the air. And here's the reason. That fuel that we're putting in there, look at the compression ratio of a compression ignition engine. It's much higher than the spark ignition engine. So we're looking at a compression ratio of 15 to 20 to 1, whereas the spark ignition engines were about 10 to 1. And so that higher compression ratio is above the auto ignition properties of the fuel, which means if I had a fuel air mixture in there, when that cylinder was coming up, that fuel would ignite before it got to the top. But I'm going to allow that fuel to get up to the top, allow that air to get up to the top. I'm going to compress it to a much higher pressure than what I do in a spark ignition engine. And now when the pressure is high, I'm going to inject the fuel into that compressed air. And so I have a very high pressure injector, a fuel injector, that injects the fuel directly into the engine. And it has to atomize it, and there's a lot of design work that goes into what is the nature of that injector. What pressures do I use to put it in there? How do I get it atomized? How do I get it spread throughout that whole space above the cylinder? Because if I just have the fuel on one side and air on the other side, I need that fuel and the air to be mixed together, and it's not going to burn very well, very efficiently, if I don't have that mixed in there. So how we design that, and actually the design of the top of the piston will come into play as well. So we don't, in a lot of engines, we don't have just a flat top on the piston. They'll have indentations or shapes or things that are going on in there. And what the designers are trying to do is, as that piston comes up, we're compressing the air, but we also want to create some turbulence and some movement of that compressed air in that space above the piston, so that when I put the fuel in there, it gets mixed really well. It starts to burn because the pressure is really high, and I get a very efficient burn as it expands and pushes that piston down. So that's the key part of it. Okay, so again, air it's clean air that I'm pulling in on the intake stroke. I'm compressing the air. I'm injecting the fuel into it. I've got to inject it in the right way that gives me good coverage, that gives me good efficiency of burn and everything for that to come out. All right. Compression ratios, again, higher, 15 to 20 to 1, something like that. That makes it a little bit more difficult to start a compression ignition engine. They're harder to turn because when it's, I have to get the engine spinning to start it, and so it takes more energy to make that engine work against that high pressure to get it started. And so that can become a challenge with compression ignition engines. Now, I can gain a little bit more efficiency out of them. So about 40% is the theoretical ceiling on the efficiency of a compression ignition engine. And so we'll look at that, and again, we come back to the PV diagrams. We'll talk about why that is and the difference between the spark ignition and compression ignition engines, and how we can get more out of it. Okay, again, the fuels that we use, I didn't mention, on a compression ignition engine typically is diesel fuel. And so that's all of our agricultural tractors, unless it's a very, very small utility tractor, everything that's got any size to it all runs on diesel engine. Of course, all of your over-the-road trucks run on diesel engines. And we'll look at performance in a little bit and talk about why diesel is better suited for field type operations like that, where we're using a lot of torque and we're pulling heavy loads, as opposed to your automobiles and so forth. Okay, so that's spark ignition, compression ignition, basically how they operate. Let's take a look now at, we've talked about 4-stroke engines. I want to take just a few minutes and talk about a 2-stroke engine, because there is a such thing as a 2-stroke. So in a 4-stroke engine, that's the same animation that you see on the left-hand side there. That's the 4-stroke engine. The 2-stroke only has 2 strokes. So for every time that piston comes down, I'm getting a power stroke out of it. So I'm burning fuel and the fuel is coming out of it. So let's look at the difference of what's going on. The difference is the chamber in the bottom. So focus on the chamber that's down in the bottom here. We actually have our air-fuel mixture in that chamber. And so what's happening as that piston comes up, you can see as the piston goes up, we're actually going to create a negative pressure in the chamber. And you can see on the right-hand side, there's a green arrow and there's a little flap that opens up here that illustrates pulling fuel into that chamber. So when we draw a vacuum, when the piston goes up, we pull the air-fuel mixture into the chamber below the piston. And now look on the left-hand side of that piston, you can see there's actually a passage around the piston. So when the piston comes down, now we close this flap, we actually pressurize this fuel a little bit. When the piston comes down far enough, it opens up this passage and allows this fuel to rush in. So that's how I get the clean air-fuel mixture into the combustion chamber. I compress that fuel, I light it, and then it comes down. Okay. Now you notice that there's no specific exhaust stroke like there is on the 4-stroke engine. So I need to rely on this clean fuel coming into the engine to push out the exhaust fuel out of the right-hand side of the engine. So that becomes a little bit more of a challenge to me in terms of how to manage the emissions. Okay, so a couple things about 2-stroke engines that we need to understand and think about. Why do we use them in the first place? What's the big deal? What's the advantage of a 2-stroke engine? For one thing is power density. So think about it. For every rotation of the crankshaft, I get a power stroke. So think about your bicycle. That's every time that pedal goes down, I'm pushing down. So I'm getting power out of it to move my bicycle forward. With the 4-stroke engine, one of those downward strokes is my intake stroke. So that would be analogous to on your bicycle, I'm only going to push down on that pedal every other time. So the second time the pedal comes around, I'm not going to push on it. I'm just going to sit there and let my foot drag on it. And then every other time I push. So I get half the amount of power out of it, or out of the energy input into that rotating shaft. And that would be silly to do on a bicycle, obviously. And so in an engine, we have that same kind of analogy that with that 2-stroke engine, I get a power stroke every time. Okay, so it's more power dense, so I can get more power with a smaller engine. Therefore, you see them in a lot of off-road motorcycles and stuff like that. They use a lot of 2-stroke engines because they're small and light, and so racing and so forth, I can get a lot of power out of them. We also see them in small engines, like in chainsaws and string trimmers and stuff like that. Again, it's something I have to carry and lift and manipulate. The lighter I can make that, the easier it is for the operator. So that's one of the advantages is that they're very power dense. You can see that there's no valves in them. Okay, so like on that left-hand side on the 4-stroke engine, I have those valves on the top. I have the camshaft that rotates around. It has to rub against the top of those valves, and so that's going to create friction. I'm going to have lubrication up there and think about how I lubricate that. All right, I don't have those moving parts on a 2-stroke engine, so it's a little bit simpler. However, look at the area underneath the piston. So in that 4-stroke engine on the left, you see, and it's kind of shown in the bottom there, you can see that green well of material. That's really motor oil. So you have to put motor oil in an engine, lubricating oil, and it would actually be a little bit higher than that in an actual engine, and it would be splashed and all around in that chamber underneath there. There would actually be a pump that would move that oil up to the top of the engine to lubricate those camshafts and everything on top of the engine. So in the 2-stroke engine, I can't put oil down there because that's where my air-fuel mixture has to come into. So what do? I have to mix some oil in with my fuel. And so with a 2-stroke engine, again, motorcycles, chainsaws, and so forth, you see them in some marine applications, on outboard engines, on boats, a lot of 2-stroke engines. You have to mix an oil with the gasoline, and that's what provides the lubrication. So that air-fuel mixture that's in that area underneath the piston around that crankshaft, it carries some lubricating oil in it to lubricate all those parts. Now, what are the implications of all of that? So I've got that oil in the fuel, so that oil is eventually going to get up into the chamber. And what happens when I burn oil? It makes smoke, it stinks, and it's bad emissions. Okay, and so 2-stroke engines, because of the fact that I have to have the oil, the lubricating fluid in the fuel, and because I don't have a separate exhaust stroke, so I'm relying on that clean gas to push the exhaust gas out of the cylinder, and the timing on that is very critical. I'm not going to have a clean exhaust of the gas and then only clean fuel in that cylinder, and so there's going to be some lower emissions. Because of that, a lot of places, two-cycle engines are being phased out. In fact, in the state of California and other places, they actually prevent the sale of two-stroke engines. And so engineers have to come up with designs of engines and so forth that are four-stroke that can be cleaner then, so that we don't have the same kind of emission problems that we need to deal with there. Okay, so again, power dense, no valves, very simple engine. The bad news is we've got a lot of emissions and everything with the two-stroke engines. So that's where we're going to be phased out. Now, the interesting thing, and I'll tell a few stories throughout this course as well, but you look at that engine there, that two-stroke engine, and it'll run forward and backwards, both. So I could actually get that crankshaft, if I could run it the opposite way, that piston still moves up and down. The direction of that crankshaft rotation really does not affect the operation of that piston. So I can actually make the engine run backwards. In fact, I had a friend growing up that had an old motorcycle with a two-stroke engine in it, and it was never in really good shape. He was pretty rough on it. And the one time we started him up to go somewhere, and he said, "This thing sounds funny." He put it in gear, and it went backwards. It actually came underneath him, and because the engine was actually running backwards. So he shut it off and started again, and it started and ran forward. So that can be a possibility. Now, the timing, the way the spark is timed and so forth, they won't run well backwards because they're designed to run forward. Again, that spark happens a little before that piston comes to the top, and so if it's running backwards, that spark would actually end up happening a little after that piston, and so it doesn't run well, it didn't sound good, and so forth. But that is one of the possibilities that we can. So, talked about two-stroke engines, four-stroke engines. We've looked at the functionality a little bit, how they work. We're thinking about how we get this fuel. Again, it's a thermal recovery. We take this fuel that has thermal energy, we're going to ignite it, we're going to burn it, we're going to utilize the properties of a fuel that's burning, that it's going to thermally expand, it's going to get hot, and we're going to recover that energy out of it. Let me show you one more thing, and we'll take a little break here. But if we look at multiple cylinders, and again, we've been talking about just one cylinder. A lot of our engines are multiple cylinders, and we have a lot of different configurations of those. So I've got a couple animations here to kind of give you an idea what's going on. The one on the left is what we call a V configuration. So you can see the pistons kind of coming out in a V shape. And you can kind of see the crankshaft there that's offset. So it's like a bicycle with a whole bunch of pedals on it. A lot of people sitting side by side on a bicycle pedaling, and in this particular case, 8 people pedaling a bicycle, if you will, or I guess 4 people with 2 legs each. So that's a V configuration. The one in the middle there is an inline configuration, so you can see all 4 pistons, and that one, that's a 4-cylinder engine. All 4 pistons are up and down. That one actually shows you the firing sequence, and so we'll try to fire these pistons alternately so that we get a smoother running engine, we have more continuous power, and so forth. So you can see that they fire, and if you look at the left-hand side there, looks like we fire piston 1, and then 3, and then 4, and then 2. So that would be the firing order. We talk about the firing order of that engine. That would be, again, 1 on the left, and then 3, and then 4, and then 2. So that's the way that they would work. Another thing that I'll point out on that is shows a belt on the left-hand side there that is running from the crankshaft at the bottom up to those 2 camshafts on the top. And you'll talk about an engine, people will say, "Oh, I had to replace the timing belt in my engine." That is the timing belt. This animation kind of shows it sort of looks like a rubber belt, and some engines they do use rubber belts, but usually it's a metallic, more of a chain type thing, and we'll look some of those later in the semester, some of those devices. But that's the timing belt. The timing is very critical because that controls when those intake and exhaust valves open and close. And so that chain has to be carefully installed. The timing of it, the relative position of those shafts and the relative speed have to be very precise. And so when that belt starts to go bad, then your engine is not going to run very well, and that's when we have to replace the timing belt in an engine. Now, the last one on the right there, I show you just for fun that we can have all different kinds of configurations. That's a radial configuration, so you can see the old airplane there, and you've seen those engines on the front, and the pistons kind of coming out radially. So that's a radial configuration, and they can be configured a lot of different ways. So we can do a lot of different things with engines there. So that gives you an idea of how we put all these cylinders together, what the dimensions are, how they function. So we'll take a short break here, and the next module we'll come back and look at how we control these engines, and that's really going to get us into what we're going to be measuring in the laboratory in terms of the dynamometer.